what I said, one of our projects, and that was also an example of humanitarian engineering in action, also from a research perspective, was basically the EduBox project. That I think was one also the contact point that we had when we wrote down the Mystic grant together. Basically, the EduBox project is a mobile learning environment that was designed, engineering, manufactured by us for bringing education to underserved communities, specifically focused on refugees. Okay, so the project was developed by the University of Twente, by us, together with Yarmouk University, that is a university in Jordan. Have you ever been to Jordan? No, it's a beautiful country. Yarmouk University sits in the northern part of the country, really also in a beautiful region, but really close also to one of the largest refugee camps that in that region. It's called Zaatari camp. One of the, let's say, problem, well, there are many problems for sure, but one of the problem that was most of the time not really looked at was that people in the refugee camps is not a temporary situation most of the time. It becomes a permanent situation. The Zaatari camp is 20 years old. So that it's really true. There are people that were born there and they are still there. So it's not something that you say, okay, it's a temporary for solving a humanitarian aid problem. It's something that is becoming kind of permanent part of your life. One of the issues is the education part, because of course, sheltering is important, water access is important, but if you think about on over 2, 3, 5, 10 years, yeah, you need to provide education also to the people that are there. And education needs to change because schools cannot be static. You cannot have people at a primary school for 10 years, right? You have to upgrade. One of the problems was that there are not many schools, so the idea that we had together with Yarmouk University, that has a research center on refugees, was to have a sort of mobile classroom that could be sort of serve as a kind of dynamic hub for different type of education, from primary school to, I would say, vet training, so vocational educational training. So for more professional, if you want to become a plumber or an IT guy or girl, and so on. Okay. So the project has been funded by NUFIC. NUFIC is part of Ministry of Foreign Affairs in the Netherlands, and we got this grant together with the Yarmouk University. And the EduBox was part of the project. Was one of the work package. So it was the sort of the let's say more tangible part, while the first part was creating the curriculum for this type of communities. The idea starts from, well, the idea is not original, let me tell. Okay, it's a container, so there's nothing rocket science out of there. But we get inspired from different solutions, and there was not that many, let's say, education-oriented container-based solution at the time when we did it. And I think was in, actually we started during COVID. Was 2020 or 2022?
I think it's from 2018, but
yeah,
EduBox we developed a little
21,
bit. Yeah.
I think, or so.
20.
So the what I want to tell, really, in a bit in short, is basically the design and the research that we went through and the different steps. Okay, because of course, as you can imagine, if you sit in a specific place and you are not in the place which you are designing things for, then a lot of things can go wrong. So the initial discussion was also with part of the communities and with Yarmouk University, that was have access to the community itself, was to identify the needs. Okay, what is the problem? Okay, the problem was that most of the refugee doesn't have access to education, to different type of education, for many reasons. We should analyze the function of a possible solution, right? What function we need to provide with this design? What is important that the solution will give, okay? In terms of, for example, I don't know, connectivities, in terms of space, in terms of mobility, and so on, right? And then when you get there, you want to have a sort of set of requirements that will guide you and guide us and the students that work with us in order to design and start the design process, right? Are you familiar with this design process by any chance? Is something that have you already seen in some courses, or have you used it maybe already even? Yeah, I think it's quite of standard part that to design. Next to humanitarian engineering program, we have access. We teach in industrial design engineer at the university, and especially in the bachelor, our students, they went through different design research method, design approach to design objects for communities, but for industry and so on. Okay, from there we move to a concept generation, all done with the students. We select one concept. We make all the engineering steps necessary for it, from calculation, documentation, technical drawing, and simulation, and then we come up with a first prototype, and then what? And then we have to manufacture it. So that was also the hard part, because it was slightly after COVID, and was quite difficult to have the hands on some materials. I don't know if you remember that time, and so on. So we manufacturing at the university in one of the workshops that we have, and then finally we're able to finalize it and send it to Jordan for the test phase, where actually is still there. So what was the starting point? The starting point was pretty clear. We used the SDGs number 4, Sustainable Development Goals, about education, right? Education represents one of the essential building blocks of our society. And that's why we're starting from with this project, right? So the EduBox was meant to basically provide access to the people that didn't have on a specific context, and the context was the refugees. We put together a team. We did it at a university, so we had Nina and I and Peter, that is our colleague in our group, were already there. And then we had a lot of students, because going back to the question that you had about the driving forces of the master program, students were one of them. So when they heard about the project that we had, there was a lot of students from, as you can see, different study. ID, it means industrial design engineer. ME, it means mechanical engineer. And then we had students that were exchanging at the time from different countries that help us in the project at different level, okay, from the design till the manufacturing. So the very first part, as I said, was the problem analysis. The needs was facilitating the physical access to education for refugee and forcibly displaced people, okay. Talking with the community, talking with the University of Yamuk University and our colleagues, some of the set of requirements we came up were really high level. I will not go into details because we don't have time. It's not interesting for you. But the first set of requirements has to be a foldable systems with table and chairs and other, let's say, tools and equipment for giving a lecture. Everything needs to be attached to the box or to the container. Should have also a small learning lab next to the class, let's say, classroom space. From the energy perspective, needs to be independent, as you can imagine, because cannot be all the time attached to a grid, because there are also grid over in that kind of context is not always available. Has to be energy independent, as I said, and also be resistant to different weather conditions. Okay, Jordan, we are talking about a climate, do you think really cold or really warm? Warm. Usually Jordan is a warm country. And we are talking about a metal box, okay? So you can already start thinking, imagine what can happen inside, right? But it can also be that the EduBox itself as a concept can be moved in a country that is really cold, or also really with a lot of rains, okay? So has to be condition proof. And then it has also to have internet connection. Why the internet connection? For many reasons. One of the reasons is that to provide education, you usually also need a trainer or a lecturer or someone, right? Someone that sometimes cannot be there, cannot have access even to the refugee camp, because getting to the refugee camp is not like getting into the train station. You need to be clear, you need to do it in advance. There are a lot of contingency. And one of the requirements was we want to have the students be able to set up the class and also to be able to take the lecture from online, okay? we came up with this brilliant concept idea that is not really innovative. As you can see, that we start just catching some of our idea, thanks also to our students. As you can see, we said, okay, this is what we have. We should have something to open the box, not only from the front door, and having some solar panels, some tables, and so on. This was really the first sketch that we put together. Okay. Then we move from there. And I said, okay, let's try to find some brilliant industrial design engineering students that can help us with that. As you can see, this was the first idea that we put together after the sketches. Okay, there is already a big difference from the previous picture. Have you noticed it? Beside the fact that it's a better picture, there is a specific concept that is different from what we envisaged.
Can you go back to it?
Sure.
It's not like the way how the box is.
Yes, yes. So this we said at the beginning. He said, let's open it like the wing of something, and then we move from a different concept. Say, let's try to be more clever. What do you think was better solution than the previous one? Is better?
It might be better because in the previous, on the first draft, like how do you hold the weight of the wings?
So there are some, let's say, structural issues that might be to lead to unsafe situation. These are quite heavy part. We don't want them that they crash on top of the students they are trying to study, first of all. So, and then there is another solution, another reason for that. What do you think might be the improvement? Yeah?
So it can be attached to the ground?
Yeah, can be attached to the ground. It can serve as a floor. And then we have immediately way more, basically 3 times of the space that we had only. Okay, so then we start saying, yeah, maybe this is the right solution. We should try to move from there. The initial design, as you can see, was using, you can see barely, but it was using a standard 40-foot container. So it's 12 meters long, pretty large. We decided for the prototype that we have to build that was a bit too ambitious in that sense, having a 40-foot container to dimension and so on. So we decide to create the prototype using a 20-foot container, so 6 meters long. And with this configuration, basically this, you can imagine that is about 2 meters width, and with 3 times is about 6 meters. Okay, 6 meters times more or less 4. So it's a 24 square meters that we could have hosting 15 students. Then we had to run some calculation because having this opening required quite some big cut in the structure. Container are made of cotton steel A, that is a specific type of steel, and we want to make sure that the structural integrity of the container was still there, because we have to move this container, need to maybe put it on a stack, on a ship, and that's to be, and so on, right? So we had to run some of these simulation and structural integrity part using FEM models, but that was the easy part still. The difficult part came when we said, okay, this is, as you can see, is already a container is shorter. This is the real one that we used. How do we open this part? These are 2 meters by 4, cotton steel with some floor inside and some metal to reinforce the structure that we cut. Those are about 300 kilos each. It's quite some weight. Clearly, they cannot be lifted by people, students, and so on. So we need to find a clever way. There are how many ways we could have without going ballistics? Do you have any idea about that? How can we open it? Which system can we use?
I'm sure there's a manual way.
A manual way? Very good, very good.
The best way to do it.
Manual way. Manual ways was the first one that we thought. So with a sort of different leverage with a chain that could have worked. Then
Laser cutting type or more technological way.
no. Let's just focus on the opening system.
Oh, the opening. Oh, okay.
we could have an oleodynamic system, basically, with some pistons, with a pump, and then there was the third one where we decided to go, was the electric system, so the linear actuator with a motor and with electricity. We decided to go there. Just to cut the story short, the manual part, we were scared that this chain would have been at some point be stuck, and they were not able to lift it. The oleodynamic system has a critical system that is a reliability, so it needs a lot of maintenance, and one of the requirements was that it should avoid maintenance. So we went to the linear actuator, the one with electric motor, that by nature they are quite reliable as a system. So we had to engineering and ask a company to produce them. And then we start from the prototype to the manufacturing. So by the way, this is Nina. on top of this is the moment where the container arrived to our university, and then we start cutting with the guys of the workshop and to make, yes.
Yes, in the first conceptual design, you guys had the solar panels above.
Very good.
Like, how do you decide how many panels or the dimensions of the panels?
As you can see already in the 3D model, we still had this setup for the solar panels. And why do you think this was the original one? Do you have any ideas?
Those look much bigger than the first.
It looked much bigger, so we could have more solar panels, and it could also decide the angle. And based on the angle, you can have more performance on the solar panels, as you know. But while we were prototyping it, we said, look, the point is that we cannot plug in, plug out the solar panels all the time, because the plug-in system is made to be plugged in, and that's it most of the time. So if you want to move it, you have to remove them, and most of the time the connection will be broken. So we decide let's say we can trade a bit of power that was coming from but we want to have them attached on the roof with the hook free in order to be lifted and move around without problems. That was a good. In total, we had, I think, 6 solar panels. Each of them was 400 watt, so it was around 2.4, 2.5 kilowatt power and was enough to let's say power the linear actuator plus all the facility inside, sockets and board. But was not enough. We also include some battery in it, in the back of. So this part was supposed to be a lab. Then we realized it was a bit too short, too small to do that. So we decided to have a technical room where we could have all the technical things, the switch box and so on. So this was where we were building it also during the night. The switch box and the insulation, because coming back what I said before, is a metal box, can be quite warm inside. So we decided we had to make it, let's say, also insulated and so on. This is a screen of the inverter that is here connected to the 2 lithium-ion battery that we use for power the edu box whenever there is no sun. Okay, so these are enough to power the box for 1 day and close it up. Then when it was realized, we moved it first to Eindhoven, where we have the Dutch Design Week every year at the end of October. Is a big event, and the university use it as a sort of home for the university. And then we ship it in this part. Here is Irbid, actually here, and this is the Zatai camp. This is the Jordan map. Okay.
Just
Yeah. Yes.
when you were developing this, did you use the concept of reverse innovation, where you'd actually go to the site and just build the prototype based on the availability of the materials?
Good question.
On the ground, because there's like studies or like well-intentioned projects, for instance, in India, where they give
Yes.
like medical equipment to rural areas, and it works for like 2 months.
6 months and then
it breaks
nothing.
down.
Yes.
So they do this concept in order to like, how can you fix it based on existing?
So basically,
infrastructure?
the only material that is not, let's say, available, let's say, in Jordan is the part that connected to the battery. that all the other parts are electric parts. They know how to fix it, and they have parts available. It's a very good question, because now we are realizing, and then I will go to the next slide, a specific edu box called manufacturing box for producing plastic bricks from plastic waste. And we developing that in a specific country in Africa, in Ghana, and we are looking about the material availability there. So will be built there. The reason why we decided to build it in the Netherlands, besides there was COVID, so we could not fly there at that time, was because it's the prototype we want to see, to have control of it at the beginning. So basically having input from all the community and the stakeholders, and then engineering the prototype. So that was our design choice at the beginning. Then when we brought it to Jordan, after that we decided we are still working on this project in two ways. We are developing the agri-box that is more focused on agricultural environment, basically what we call. As you can see, is still on the concept, at the concept level, where basically there is still the container that will serve also as a classroom, but we'll also have a water reservoir as a thermal buffer, as a shading part for growing seeds and so on. And for that we won the first prize at Siemens in Munich. And then, as I mentioned, we have the manufacturing box, so more a portable learning environment for sustainable manufacturing. Different type of manufacturing. The one that we are at the moment working on is for recycling plastic and creating plastic bricks for building, basically, project. And the one that we are working on is for washroom in Ghana, next to a school. And for that, our students, they first award engineering day last year in 2025 from UNESCO. I think I have also a video. Yeah, it's in there. But you cannot.
Poverty and plastic waste are deeply interconnected challenges. With over a billion people living in substandard housing, many lack access to proper sanitation facilities, impacting their health, dignity, and safety. At the same time, plastic waste piles up, blocking waterways and polluting communities. These settlements often rely on makeshift structures that cannot withstand harsh weather, leaving residents vulnerable and in perpetuating cycles of poverty. But what if we could turn this plastic waste into opportunity and contribute to the challenge of access to affordable housing through building materials made from recycled plastic waste? We can empower communities, reduce poverty, and create jobs while transforming informal settlements into safer, healthier places to live.
Introducing the manufacturing box, a self-sustaining microfactory that converts plastic waste into building bricks, thereby supporting communities in creating jobs, bricks to build houses, and reducing plastic waste simultaneously. Our solution is inspired by the EduBox, developed by the Humanitarian Engineering Group at the University of Twente and a current project of Engineers Without Borders NL and TrashSmart. Here is how it works. Plastic wastes get collected at schools or by local waste pickers. PVC gets sorted out by hand, the remainders get shredded and cleaned. The cleaned plastic shreds get melted and mixed together. This mixture will be molded into bricks using compression molding. The entire system runs on solar energy. The bricks produced in the manufacturing box can be used for proper housing in informal settlements or build washrooms for schools in the local communities. And with this, provide education on the value of waste and create better sanitation. The self-sustained microfactory will create job opportunities, generate a local waste management system, and educate people on waste being a source of material and not just litter, creating a self-sustaining and a self-improving loop.
The recycled plastic bricks are the cornerstone of the manufacturing box. Using CAD software, the bricks have been carefully designed to use as little plastic as possible. Only 1.3 kilograms of plastic waste per brick. The bricks are manufactured using low-cost and low-tech machinery and laser-cut molds, suitable for solar-powered shipping container factories. Through compression molding simulations, we optimize the production process, ensuring that every brick is efficiently molded with minimal material waste. Our team conducted stress simulations to guarantee that these bricks are not only lightweight, but also capable of withstanding structural loads for projects like housing and school washrooms. Lighter bricks means less strain, enabling a safer and healthier work environment for construction workers. The interlocking design of the bricks allows for a quick and easy building process, which has been tested using 3D printed prototypes. The manufacturing box also has gone through various iterations in manufacturing simulations to ensure efficient layouts and optimal tab distribution, enabling a high throughput of only 4 minutes per brick. The costs for setting up a microfactory are estimated at a small €15,000, a significant but accessible amount for local entrepreneurs.
Our solution will have impact on several of the Sustainable Development Goals. By using these bricks to build washrooms for schools, we have an impact on gender equality, since more girls will be able to attend school when proper sanitation is available. This proper sanitation in and outside of schools will also have impact on clean water and sanitation. Furthermore, the manufacturing box will create decent work and job opportunities, which turns into economic growth in underserved communities, impacting SDG 8 and 9. The recycled plastic bricks, sustainably produced, will help build inclusive, safe, resilient, and sustainable communities. By improving gender equality, building better sanitation, creating decent work and job opportunities, contributing to economic growth, and creating sustainable communities, this solution is a small step towards achieving the Sustainable Development Goal number 1, ending poverty, brick by brick.
So basically, as this was the first step, now we are building, basically we are running this project together with Ghana Engineering Without Borders, and we will build also at the same time one space at the University of Twente with a plastic and plastic bricks, and one in Ghana. Of course, different type of space because with different needs, but we really want to have this kind of one-to-one collaboration that's going on. Students from Ghana will come. One of my students is going there in a couple of months, and to have this kind of solution together. There are some drawbacks. It's not everything is gold, so to speak. Having a container, it's sometimes an issue because not all the roads can be used to bring a container. You need a truck anyhow, and a sort of a truck with also a small crane that can unload the container of the truck. So it's not possible to use it everywhere. If it's really hilly, it can also become an issue. So it works very well in a place where it's flat, and you can have also sort of flat setting. Otherwise, for example, the doors that I show you, if the container is twisted, they can have some resistance in opening and so on. So it's not perfect by any means. Yeah.
Yeah, I've heard about this plastic recycling a few times before, and I was kind of wondering about the fumes and emissions. I always thought that might be dangerous to people who actually.
Absolutely. Yeah. There are different technology. At the moment, what we are looking is not using only injection molding solution. I don't know if you are familiar with that. Basically, you melt it first, and then you inject it in a machine with high pressure with a mold of the shape that you like. Okay, but it's also a very expensive machine. First of all, it requires a lot of energy, so it's not really particularly fitting for, let's say, constrained energy scenarios. So what we are, the students that was in Ghana last year, we decided to try it a different way using just an oven to basically melt it, the plastic, and then put it on a normal mold. I agree that there are some concern about the plastic. The brick is not 100% plastic. You have to mix it with sand. And we are developing together with Engineering Without Borders and Delft University a recipe, because only plastic might have some issues in terms of structural integrity and resistance, or if you even think if it's really warm weather, might even lose a lot of capability due to the warm weather, right? So a sort of a percentage of mix, we are still going for it, and we're adding sand to that. In the video, I think Gert, the guy, told us about the interlocking system, where the students was working specifically on that to avoid that there are some sliding between the bricks. We are even thinking to have some all in the brick, so if you want to have some steel bars and add a bit of integrity to the wall, especially if you want to go to two-story building, it might be needed. So that it's a working on project, and we have quite some students are working on it, so it's quite promising. let's see where we go from there. I think we have a break now. We were a bit behind the schedule, but I think we can catch up.
Maybe you could do a shorter break.
A shorter break, yeah.
We
Like
just also have to set up the game, so I need at least 15 minutes to set up the game. So.
okay, yeah, we can have maybe we said 30 minutes. We can have max 20 minutes, and we're also setting up the serious game.
Yeah.